Hello, welcome to the fourth lecture on the Calculus 1. Oh, well, as I recently realized, what I'm doing here is actually not Calculus 1, but it's Rio Analysis 1. I just didn't know that the English words calculus and analysis, no, to begin with, I didn't know that there was an English word analysis, and even if I knew that, I thought it was something different. And then I thought that calculus is uh, what people usually call analysis. And yeah, I had that confusion, and so I called the course calculus, but actually it's analysis. But yeah, it seems that different books with titles in different languages that would actually not be books on calculus, but actually books on analysis are translated with a title of calculus, for example, the book by Prusuing or something. So I think it's not much harm. It's not about what it's called, it's rather about the contents, right? Okay, I hope after the last lecture you realize that the uniqueness of supremum of a bounded from above set in video numbers is pretty obvious. It's basically almost a definition, but let's make a note. Doesn't deserve any proof or something. Note for an M subset of R bounded from above supremum M is unique and this is just due to the following. This is just due to the following. Well, that is still the cos supremum M. And supremum M by definition was the least upper bound. And as tilde are both upper bounds of M. And by properties, by respective properties, by respective property of being the least upper bound, obtain, well, if S is the least upper bound, then S is small or equal any other upper bound, and vice versa for S tilde, which implies S equal S tilde. Okay, so Suprema are unique, and where were we? Well, we have finished the proof that 1 divided by n, respectively 1 divided by n plus 1, depending on where we start in natural numbers to make the sequence defined, but the essence of the sequence in sense of limiting behavior stays of course the same, because we are only interested by what happens in the limit, kind of at infinity, that this sequence converges to 0. Okay, and now we have the standard properties of the limits. I think we should be already able to prove them, and that is called arithmetics of limits of sequences. And you probably already know what we are about to talk about, arithmetics of limits of sequences. But if no, then enjoy the journey in this new landscape. Arithmetics of limits of sequences. Okay, well, and I guess that by this theorem I will have real struggles by one point because I totally don't know how to prove it, and this will be completely spontaneous derivation. And well, let's just take a look at it. Okay, well, let um, an element n, bn element n. Well, let's do it differently. Bm m element n. For the case if we need somehow to distinguish when we are talking about the members of the one sequence and of the other sequence. So let's distinguish that. But of course, since it is two different mathematical objects, we could have kept same index and just distinguish that afterwards. Doesn't matter much. Okay. B convergent sequences. Convergent sequences, recall that convergent means a limit and that means the limit by uniqueness of a limit respectively exists. Convergent sequences of real numbers, of course, as always. We don't have anything else in our setting with respective limits. With respective limits, A and B. By the way, let me remind you that if it's going to slow, then just double the pace of the video and then it will be fine. I checked it myself when I'm rewatching the lectures that I made to spot mistakes and things like that. To just see what came out of it. I'm actually watching by double pace because it's too slow for me to. Okay, with respective limits a and b, then how such a sequence we can define. Okay, would be maybe a little bit more self-suggestive to use same index after all, but you understand we are actually going through all natural numbers. It doesn't matter what we call them, it only matters through what we go. So this for 0 in n will be just a0 plus b0, and that here n takes this value of 0, here m takes this value of 0, doesn't matter since we just go from those, and those are just names of going through those, so the names itself don't matter, right? Okay, there's a convergent sequence, and then let's code 1 is a convergent sequence. And let me make a short remark. Of course, a minus bn, a n minus bn is just same thing where we just add inverse of that sequence. But okay, it is not completely obvious yet that it works. It will be obvious that it also works for minus after the second property, where exactly multiplication with a scalar will be considered. Well, Okay, a sequence versus sequence with a limit. Well, you can guess. If that approaches A, that approaches B. Well, what could that approach? Of course, A plus B with sum of the respective limits. So this with minus will be obvious after this property. If C and actually, what am I doing? Oh, we don't need to consider that particular case. We can phrase it more generally. That's what I mean. And if okay, then I don't need if also. Okay, and multiplied by bn and element 10 is a convergent sequence, and you can guess again what is the limit of that with a limit a multiplied by b. Okay, and here what I wanted to discuss short, well, just recall that for x in your numbers, that is what you had to prove, and we have had that already on multiple occasions. Just think about the sequence minus 1, minus 1, minus 1, minus 1. So it's a constant sequence. There's no problem with that. We could define map that just for each n element and gives that n constant numbers, so we are kind of staying at this same number, and by n steps, by one steps, we're just staying at the same number. So yeah, can be. Okay, if you now imagine sequence Alright, we want to consider the difference here, and now you imagine that your an here for this property is chosen like that, and if you multiply bn like that, and you get exactly the sequence minus bn, and then by this property, and you have those both, then you have these both properties, then you just can put here an plus minus bn, knowing that minus bn converges to minus b by the second property, and then you just get that the limit is a minus b. So actually, there is not necessarily need for such explanations. It should be self-explanatory, or respectively, you should be able to discover it by yourself, but nonetheless, I'm just explaining that to give you a little more sense of how thinking about such things can uncover, and to make your mind engage more with that matter. If additionally, third property, if additionally bn is not equal to 0 for all n element n, and again you can think that we have shifts of sequences, and if we have a sequence that has only finitely many members that are equal to 0, then if we wish to build such a sequence, we could shift this sequence to the member from where onward there are no 0 members anymore, and then we could consider such a sequence. And if additionally we have that for the sequence under consideration, then n and by bn and then is a convergent sequence with a limit a divided by b. Okay, let's do the easy ones. So obviously b cannot be 0 if we have that b ends are not 0 respectively. Uh, oh, sorry, it actually can. It actually can because it can approach 0. So secondary and additionally, because yeah, 1 divided by n, nothing is 0. Okay, and b is n equals 0. Mm, n divided by b and then it's convergent sequence with the limit a divided by b. Okay, let's think a little what happens when b is equal to 0, but none of those are equal to 0. Could we still have a convergent sequence here, albeit not with this limit? Uh, if that is equal to 0, then of course it's bn will approach 0. Okay. This is how you write the sequence converges to 0. Or you could also write that, but now it is clear because we only have this index as a dependence mark of something. So yeah, but I could have written that below or above, as you like. Okay, well, I think that's not quite true, for example. So yeah, there would be, one should be careful. There would be different cases. I guess you can say that this sequence converges to 0 too. But you can prove that if you like. The proof is fairly similar to that, but you could just prove another lemma that says that actually sandwich lemma we didn't have, yeah, so you would have to prove directly. Okay, I will think about where to we need sandwich lemma. It's so we will need a special lemma about sequences at one point, by which you could prove it easily that this also converges to 0 when you have that this converges to 0. But okay, for now not. And this converges to 0. This converges to 0, but this converges to 0. So when we have that this limit is 0, right? It doesn't mean that the sequence doesn't converge, but that means you can see here limit is 0, limit is 0, so we can't reasonably apply a theorem. So the theorem is only stated indeed for this case when the sequence is not equal to 0 everywhere and where b is not equal to 0. Alright, because obviously we couldn't state it for b equal I mean we couldn't state it for b equals 0 in that way, and we could think, well, what happens when b equals 0? Could we state it somehow? And well, we actually couldn't, because on one hand we could have that, on the other hand switch the roles of the sequences, and we have that is n. Yeah, I'm just using the properties of fractions here, right? Tower fractions, but you could write it out as you wish. And this 1 divided by n. So that goes to 0 and that goes to infinity, right? Okay, so there can be multiple, there can be different cases when b is equal to 0, and that is why the theorem doesn't talk about this case. So the theorem talks explicitly about a case when b is unequal 0, but it doesn't mean that in the case b equals 0, which I doubted for a little while, there cannot be a convergent sequence. It is just that the theorem cannot but there is no definite statement about the sequence, and that is why this case should not be included in the theorem, because there is no proper theorem to state that. Okay, and actually, I guess we could, in that case, we could reach any limit we like. Yeah, pretty much. Yeah, okay. For example, such a sequence, which is just a constant sequence, but it could have arisen from that and that sequence. Okay, so yeah. Um, no definite statement here. Okay. Oh, okay. Let's prove it. Let's do first the easy ones, one and two, and then we proceed with the hard one, which I would have need to look a little bit. Okay, proof. Well, what do we have to prove? We just have to prove that the definition of limit is actually satisfied with that. And well, proof. Of course, we just let first epsilon be r, r in r bigger than 0, right? Then have to show here is an epsilon, and then we have for all and bigger or equal than epsilon. Well, recall the definition of a limit, a minus b minus, and already like we multiplying out the bracket, the brackets, right? We would have that, but actually originally we would have oh, I stated with that with plus, yes. So originally we would have, of course, that, but okay, it's obvious. Okay, well, we have that, and we would like to have that for all and bigger or equal in epsilon. And again, we use a very similar trick like the trick we used by proving the uniqueness of a limit. I just look at how we could use the triangle inequality in a proper way, well, and then we come up with for epsilon half respectively, and epsilon 2. Okay, I'm calling in that, but you know what the would really mean the for epsilon half, right? I have respectively an epsilon 2 such that for all and bigger or equal than epsilon, just using the definition of the limit of the sequences A and B, which I can because they are supposed to be convergent. Just look up what the theorem said, right? And I want to do it for epsilon half, right? Here epsilon 2 half. Alright, and here may be a remark. I'm doing that now fast, but if you need to follow through the particular steps, then just pause and think about what I'm actually doing, what I'm employing. Okay, okay. Then but we had a very similar thing where we employed the triangle inequality in similar settings, so I think that should be clear. But it doesn't mean that it has to be clear, right? Because it is abstract stuff. You might have forgotten it partly. That's completely valid. But yeah, have that simultaneously both is satisfied, and I already explained to you how it works when we prove the uniqueness of the limit. I mean, actually, it's same epsilon. Just I wanted to have different ends, so yeah, okay. That's not necessarily since it's same epsilon. I shouldn't suddenly call it epsilon tilde since it's same epsilon for which we take some half. So yes, let's take that. All right. And that would be confusing actually. But yeah, um, when you follow through such proofs, you should see the story behind that. You should not focus on particular details. You should be able to follow through particular details, but you should not focus on him, but rather perceive him as auxiliary thing to the mathematical story that is told to you. Story of to the part of the landscape of the mathematical world that is uncovering before you. You could also talk about that as telling a story, like such a proof tells you a story. And what are the particular details? Well, the thing is, the story can be only told in legal shape, because only then your thinking can engage in making that story. The special feature of such stories that mathematics tells is exactly that those stories you create with the story unfolding. Your mind engages in creating the story by design that is given by mathematics itself. So the particular forms, they are not important. The mathematics itself that is behind it is important. And yeah, and those are just particular forms in that the story can only be read by humans, because otherwise our mind would not be able to interact with the way how one has to interact with the story to read it and simultaneously create it in oneself. Everyone see a different story, but there is a common piece of information in it and a common piece of common world, because this common piece comes from the nature of mathematics. So everyone see different things, but we all agree about mathematical things because the mathematics itself is eternal and unchanging, and the way how we write it down is just the way how we write it down, right? But yeah, only in that shape, unfortunately, the human mind can interact with mathematics. But you should perceive it exactly as that, as auxiliaries. And then you should have this light touch. You should have light touch on these topics. Okay, well, for session we have that. With that, obtain. So for that n, we already have that property, right, for those objects. And for such an n, we can then, well, for any n, we can estimate that by a triangle inequality, right? And that's exactly, and you recall how the absolute value behaves, so there's no trouble when I just relocating that like that, right? Well, a plus b. Why am I constantly writing? So here using commutativity and then using the triangle inequality rate. So that's very similar to how we proved uniqueness of limit from the spirit of how we come up with a proof. And here, of course, again, plus. And you see, since I kind of feel that it is not that important how we write down the things. I'm just mixing up signs or something because I know what I'm trying to tell, and this is the important thing. So if there are such typos, and such typos you find basically in all mathematical books in truth, it's because we see what we are trying to tell, and we are not focused on what we are telling. We are focused on what we are trying to tell. And what we are telling is just before, and we are very aware of it, and you should be too, because this is the way. Those formulas and tossing around symbols, it's auxiliary. You should see the marvelous action that is hidden behind it. Yeah, okay, just think about it. Okay, well, just learn to see that as an auxiliary thing, and then you will enjoy it pretty much, even such abstract stuff, because you won't focus on the particular symbols or things like that. You would focus exactly on what they are telling you truly, in the true mathematical meaning of what is happening. Okay, what do we have thus far? With that, we obtain that, and we obtain for O and max, epsilon and epsilon tilde. We obtain that, and that is exactly what we wanted to show, right? So we found in n, certainly is just maximum, so it is just one or another, respectively, which one of them is bigger or equal the other, right? So it is a natural number. And we have for all n bigger or equal than that, we prove that this difference in absolute value is smaller than epsilon, and this is exactly what we wanted to show, right? So don't be confused by different notations. As I told you, the mathematical meaning behind it is what is important. Right? Is that is an epsilon and that is suddenly also an epsilon. Well, just learn to think, well, what is this actually really trying to tell in the context? I know it is difficult and it takes a lot of time, but um, go with that aim in mind into mathematics. Okay, but that finishes the proof, right? So, let's have a look at 2. Obviously, by 2, we can't employ such a simple proof because, as you will see in a second, and that was proof for 1, proof for 2. We have to show similar thing, but the limit is multiplication, so we have to show for epsilon bigger than 0, and to recall the convention that it already means usually that it is in real numbers. You have to show for epsilon 0 at near h and epsilon and 10 such that for n bigger or equal and epsilon have a b minus a and bn is what? Well, smaller than epsilon. Right, and now we see that our idea wouldn't work and we might not know how to proceed, right? But then we just remember that we can alter objects in mathematics in some way that gives them a different shape in the sense that we are writing them differently, which makes them apt to certain manipulations, but which doesn't change them. And what things do we know just what we are able to do just like that? No, we know what those two things, right? And I'm not saying that it is most nature to think first of that, but kind of we have an arithmetical expression, right? And we'd like kind of to use this method somehow, but we don't know yet how. And it is in nature to think, or you could say that it is nature to think how to alter the shape without altering the meaning. And this is altering shape without altering meaning. So what we could think about, we cannot immediately apply known dynamics of the things involved, right? But perhaps by some certain change we might. But what change could be that? It should be things with controlled dynamics, right? With controlled dynamics that allow us, and by dynamics I mean the limiting behavior, right? We have now constants here and we have sequences, and sequences have certain behavior, and constants are just constants, well, they are numbers, right? So what could we do here? For example, multiplying by something, multiplying by 1, right? Oh, 1 itself is not interesting at all, right? Because it doesn't change the shape. One multiplying by 1 itself doesn't give anything, but we know that 1 can be represented like that, and so that might give something. But well, when we have now some fraction made out of it artificially, we don't know a lot about sequences and fractions yet, so doesn't seem a good choice. So then let's try that. But again, just adding 0, well, we can't get much out of just adding 0. But when we think about that this is just the shape of a mathematical object that 0 truly is, we know that we can also use this shape to represent 0. So mathematically it's the same expression. I mean not a, but some, we don't know if it has to be a or something maybe more sophisticated. We don't know. But yeah, it's just something, right? And what would be suitable choice for 0? I would like to use the triangle inequality, right? And we'd like to do it with something that has, well, that would produce here something that has controlled dynamics, the dynamics that we can control in the way that we can estimate them from above, right? Because we'd like, in the end, using the dynamics of the sequences that we know, that an converges to a, bn converges to b, estimate that, right? So what would be suitable choice? Well, we should take something with controlled dynamics. So, and we should kind of use the triangle inequality. So, of course, we'd like to somehow we don't know anything about the joint behavioral sequences, right? That is exactly what we are trying to prove. But something where only one sequence is respectively present, that we can control if everything else in what we are putting into it are numbers, right? Because this limiting behavior we can control. Okay, and now I realize that we need a certain lemma. And that lemma we will have in a second. Or maybe we don't, but like limiting behavior or something like that, we can control, right? When you put something else into it, it kind of, the only that thing is what has limiting behavior, right? Okay, so what could that be? Well, with such reasoning, you just come up with that. Actually, I'm not sure now. But yeah, seems like a good thing to try, or maybe not so good. Okay, I'm not sure, but okay. So the reason that we need something whose limiting behavior we can control it, that can help us to use triangle inequality, right? Okay, then what would be a suitable choice for that? Well, let's think. I think that we should take something like that. But maybe the first one should be that. Well, it should somehow match, right? So it matches like that. So yeah, well, if we were to plug in, of course we need zeros, so we were to plug in something like that, right? Because the limiting behavior of that we can control, or at least we can suppose that we can control limiting behavior of that. Oh, this is one way to think about it. Maybe I'm not thinking about it the right way currently. That's also possible. But let's think about what we would have. If we were to put that like that, and we were to put that like that, then the thing that would arise would be here bn, and here would be bn, and here would be. Well, I'm not seeing where it leads us because I'm not seeing that we can really make immediate use of that. But maybe we are missing a lemma, also possible, and missing some statement that would help us. Okay, the problem with that would be that we cannot control that properly, right? Right. We cannot control it properly, but actually, yeah, okay, I see that. I could not see that immediately because you don't know some things yet. So yeah, that's of course problematic. Okay, well, okay, so you see, I now see that of course that reasoning is kind of valid, right? But we still need a special lemma. We still need a special lemma. Well, as you can think of that, if that approaches that, right? And we can control it by. We actually do not need that lemma, but maybe. Oh, okay, yeah, yeah, okay, okay, yeah, it works. That works, but well, um, yeah, okay, we still need something. We still need something, and that we cannot avoid. We need that is goes to 0, and that we'd like to have that because we would like to estimate that against epsilon, right? And of course the absolute values around it, we'll write it in a second, but it's just a side calculation as always, right? So that you see how one comes up with that. But yeah, to be honest, that yeah, would have been too many steps that we would have to see. We need an additional lemma, and this lemma states that a convergent sequence multiplied by nullsequence, that this is nullsequence you should see when an converges to a, and you could prove yourself that it is a nullsequence, right? This is very simple. It's basically restating. Well, it's actually uh, well, it's so simple that I don't know how to phrase it. It's like uh, when you think how the definition of this being nullsequence is compatible with the definition of a being limit of an, and we have that immediately, right? Well, of course there is a little catch because you would have to show that xn, and I just called the sequence in non-customary way, actually implies that xn goes to 0, right? But well, that you would have because okay, so we need a couple of lemmas, so it's not done just like that. Uh, but well, yeah, okay. Let's prove a couple of lemmas. I see that we cannot prove that immediately. Or maybe, well, I guess, well, the way that I see would use some lemmas. So let me put it like that, okay. And that's exactly the lemma about which I thought that we might have to have that. Okay, lemma. That is the so-called sandwich lemma. And I never knew if it is called to it's being dedicated to some guy named Sandwich, or if it is just because what we will look at will be kind of a sandwich. The proceeding that we'll look at will be kind of like sandwiching something between two things. But never knew that. Okay. Sandwich lemma. Yeah, that's a tasty lemma. Let an element n. Let's go to soda and element n be convergent sequences that have same limit. We have the same limit, so two different sequences having same limit. We have seen there an example of such two sequences where I have discussed that possible or hypothetical alterations that didn't work of the case when we lose the requirement of a limit not equal to 0 in the quotient rule for the limits. We have seen the sequence 1 divided by n converging to 0 and 1 divided by n squared also converging to 0. Right, with the same limit, let's call this limit a. So it's really custom. But now let Cn and element n be a sequence such that Cn n and tilde n for n, and this is how we sometimes write the quantifiers by quick writing. Of course, you should have written that here for n, the 2 points. This is true, right? But yeah, by quick writing, you sometimes write it like that. Let sequence then Cn is convergent, and how to what limit to the limit is convergent to the limit a as well. Right, let's prove it, and I have a feeling that for that we will need yet another lemmas of comparisons of limits, but maybe not. Okay, let me think. No, probably not. We would not immediately apply this. So probably we should be able to prove that without our lemmas, but yeah, I don't know yet. We will see. So you see, that is how mathematical process of thinking about a topic goes. You go in one direction, you see that there might be some necessities, and you check if that is actually true, what you conjectured, and things like that. But of course, now I have the advantage that I have had those courses, and so I kind of my subconscious knows the structure, so I don't have to blindly check everything uh, or well, not blindly, but without knowing the outcome. I kind of know the outcome, at least we find our outcome, but no, the intermediate steps I kind of don't know. So yeah, in a way, blindly. Blindly, but of course with a higher degree of intuition which one would have when one is confronted with a completely new topic, right? Here you could really take sideways that just don't lead anywhere. All right. Proof. Well, what would we like to show? We would like to show that Cn, okay, convergent sequence, and that is convergent to this limit A. Okay. Well, okay, let's think. Let's think about it a little bit. How could we start? How could we start? How could we do that? Okay. Well, maybe let's just try to establish some comparison because we actually have that, right? So what we are trying to establish is, okay, we actually don't have that. We'd like to have that, right? Smaller than any epsilon for true than epsilon for some n's bigger or equal n epsilon, but what we are trying to estimate isn't that, right? Okay. Well, okay, let's do this thing. What we are trying to show is actually in plus epsilon. Recall that trick, right? And that is in between a minus a plus epsilon. Okay. What we have is already Cn more equal an, and we have that, right? That we have for every n, not even starting at some n, but clearly this lemma also works when it just starts at some higher n. We know that only the limiting behavior matters, and well, of course, all the reasoning will just apply the same, right? Okay, well, and we know that those are actually estimated. Okay, it's actually very simple. It's just too simple. I cannot believe that it is that simple. Okay, okay, sorry. Not necessarily simple, but like, it's much simpler than I thought. It is not necessarily simple, it is abstract stuff, yes, but it's simpler than I thought. I thought there is like a much more difficult approach required. This approach is not necessarily simple, but I thought that something much more difficult would be required. Okay, for epsilon 0, f and epsilon 10, and epsilon tilde and 10, such that for all, well, I'm just using that those sequences above convergent to A, okay? You'll see in a second how I use that, such that for all n epsilon and epsilon tilde have what? Well, we have a minus n smaller than epsilon, and here same limit a, which is important, smaller than epsilon. But then we just know, right, Just know that from the property how we establish, how we open those absolute value brackets. Right? Just know that this is true, and we know that this is true, right? And that is how in for n bigger or equal maximum. So you see the tricks that we employ to do such proofs, they are very similar. We just have to look at what properties of what mathematical objects are given in the concrete case, but how we deal with the limiting behaviors and make them serve us in the appropriate way, the tricks are very similar. And for n, for any n, so in particular for such n, we have of course that Cn for all n's, in particular for such a's, is bounded by the respective members of the respective sequences here, right? Okay. I kind of switched that. Okay. I'm going to do differently because I had that above, so I would like to have above estimate. Right, just because here I had that above, so I would like to have the estimate from above because I'm trying to show that just by definition of what that is. So of course I need a above estimate for what I had above, meaning that is that. Okay, that is above estimate and that is below estimate because I get that below, right? Okay, and here I have that bigger than that. Okay, and I have that bigger than that. To recall this, just recall how you open that and just consider different cases. We have done it extensively, I think, in the third lecture. But yeah, and just take a look about it another time or do it by yourself. It is even better when you realize yourself that this must imply this. Right. Okay. And we did that, but if you realize that now yourself, then it's just great. Have and how that implies, because that's exactly that, right? It's exactly that. Cn minus a epsilon. And you can see that that is that because, well, if Cn minus this is in our direction, that's why I'm doing it shortly, just to convince you a little. Imagine that is positive, then we have to show that, right? Whenever that is for some n positive, then we have to show that. But that is exactly Cn smaller than a plus epsilon. So we have for all n's from a certain n, namely from n given by this max, we have that it is always smaller than that. In this case is already done for any n, right? So whenever it occurs to be positive here, we have what we want for this. So all those ends are covered, meaning that we have that relationship for all such ends where that is positive. Okay, this is just from that. But now let's say that is negative, right? And again, we open the absolute value. And what we see is, well, just bring it to the other side, bring that to the other side, and you have Cn bigger than minus epsilon. So indeed, this gives us that. So all n's are covered. For any n, we have one of the two cases, and this condition amounts to one of the two cases, and both cases are indeed covered, meaning that every n is covered having this condition fulfilled. Right. So using the fulfillment of this condition, no matter what n we choose. Okay, well, next up, Yeah, I wanted actually to let you do it, but okay, let me do it. Doesn't matter much. Lemma. Ah, okay, no, that. Yeah. Okay, one thing I will let you do it, let you do, but one thing I will do. Lemma. That's that. You wanted let. No. Yeah. You should do it. You should do it. Lemma. Let. No. You should do it, and I'll give you a hint. Use the sandwich lemma. It is for one direction. Lemma an then converges to 0. That is, it is convergent and has limit 0. It is just a shortcut to that. If and only if. I don't know if I have already introduced that notation, but if I write if, then that means if and only if, in sense of logic of statements, of course. Converges to no, converges to 0 if just same sequence, but we put absolute value to each such that converges to 0. And one direction is by sandwich lemma. Guess which one? And just keep in mind that sandwich lemma can be applied, of course, to a constant sequence. And another direction is by let me think. Yeah, another direction is by thinking what absolute value means just in terms of what we have looked at there. All right, and that is homework. Okay, and next up we will show that convergent sequence multiplied by nullsequence gives nullsequence. Okay, so that is homework. Just think about what it means. Well, one direction is by sandwich lemma, think which one, and another direction is just think out two possible cases and what they mean for certain thing. Maybe try to visualize what is happening there, and yeah, that way you'll get that. But actually, I think it's even easier. You don't even need sandwich lemma. It's pretty much straightforward, simply because the definition of the convergence is stated in terms of absolute values. So yeah, it's very easy. So do that. Do that in sense of abstraction. It might be not easy, but don't let it discourage you. Just look up the definition above and think about how to do that. It's not difficult at all. Okay. Of course, even though I'm saying it's not difficult in the beginning, I think I would have struggled with it. Uh, yeah, I think actually I would have struggled with it myself, so um, it's not saying anything, right? So the main thing is you should do it. You should look at it, you should engage with it within your mind, and you should get it, no matter how difficult it be, which could be, and which is no problem. As I told you, this is completely no problem. This is the beginning. Okay, lemma. Let's and and maybe I should remind you this point that we are actually proving all these lemmas to have this proof here, not this one, to have this here. I just realized with that reasoning that we need a lot indeed, but yeah, this is often a proxy mathematics. You come to some point and you just play around with some object and you come to some point where you realize, oh, those statements would be nice to have, and then you go and try to prove the statements. Maybe it works, maybe it doesn't work. If it doesn't work, you go a different way and try again to do something, and so on. Let a and a convergent sequence be convergent. It doesn't matter with what limit, but let's call the limit a. Limit a. Let's be an element and be a nullsequence. And nullsequence means it converges, and the limit is 0. Be a nullsequence. Then an bn an element n is a nullsequence as well, so it converges, and it is indeed, and it has indeed limit 0. Okay, how do we do that? Well, now if okay, I think we should state yet another lemma. We could have just derived that within this lemma, but yeah, it's a nice lemma and an important lemma, so let's state that lemma if a sequence an element n is convergent, and let's say again limit a r. Actually, if you want to be very precise, you try. Of course, it is not a set, but you like mean by that the set which contains all the values of the sequence is actually a subset of R. And the values of the sequence were just recall that sequence was a map. That's why I call it values of the sequence. Okay, it is convergent. Then it is bounded. And what does it mean that the sequence is bounded? Meaning that we set exactly the set of the values is bounded. That we set an element n set of the values of the sequence is bounded. Okay, and maybe I should give definition of a bounded set. Definition a set M subset of R is bounded when if the definitions are stated with if. Just a customary rule is bounded if there is tilde R such that all M element M have m tilde bigger or equal the absolute value of m, which is of course equal to m is between minus m tilde, so each m is between minus m tilde, and you can see immediately, since it is bigger or equal absolute value and absolute value is positive, just the particular m, it is bigger or equal absolute value of that, that is of course non-negative. Okay, well, and yeah, this is equivalent to that, just to think about what absolute value means and then apply some basic theorems of real numbers and you will see that. Right. So that is a bounded set M has elements, let's say video line goes somehow like that, right? And those are like representing the height, and that is now a v0, and we just go through the set M horizontally and we map those elements in that, right? And maybe we have index those elements, no matter if it is as many indices as natural numbers or more, no matter what it is, we just have that that is m tilde and that is minus m tilde. So that is what means this. Right. This could be somehow fluctuating within that, but v values always stay in this in those bounds. Right. Okay. It was just definition. That was just example. Okay. Not example, but visual intuition. Okay. And now let us prove that. Proofs again are very simple. You just think of a visual thing where you think, well, what does it mean that this set is that the convergent sequence is supposed to be bounded? Well, what does it mean to be convergent? Convergent means that to this R A we are being let's it's better to have the vertical visualization of that. You could again think of your Cartesian coordinate system, right? And this is your n, right? But okay, that's of course r, but n is subset of r, and then you just have your function which has this n values, right? Yes, it is n values, and this is r, and somewhere here you have that limit, so the far somewhere is infinity, you have that limit, and you just have that your function values, right? This is your limit a, and you have that this is function, right? 0, and sequence is a function a0 somewhere here. You have a1 somewhere here, right? Sequence is just a discrete function. We talked about sequences being functions, so think about this graphical mapping. It is completely natural thing. A2, that is 1, 2, 3. It is kind of discrete function, right? We can visualize it like that because well, it makes perfectly sense, right? And then in here, you just have that you it is kind of at infinity. I mean, that is at infinity, that it is kind of completely, completely near A, right? So this gets very, and for all things from such, from some and onward, you are in this epsilon neighborhood, right? So for infinitely many things from some and onward, by definition of convergence, you are in this epsilon neighborhood, right? This is a plus epsilon. I mean, this here is a plus epsilon kind of, and this is a minus epsilon, right? You are in this neighborhood. It is for infinitely many, And so what remains here is of course finitely many, because those are just natural numbers smaller or equal n. And for all natural numbers bigger or equal n, we are in this, right? This is the intuition behind the proof. And now do we prove? Well, since let, and we just take any epsilon bigger equal 0, let epsilon r bigger equal 0 or chosen fixed, because we don't care, we just have to show boundedness, not boundedness for specific bound, we just have to show boundedness. So let's take just some epsilon, just have to bound all elements, right, by some real number, no matter how big. So chosen fixed, then there is an epsilon, and then such that for n bigger or equal than epsilon, our distance of a minus a n is just more than epsilon. And that means exactly being here, right? Okay. And of course, if we take m somewhere, so that this finiteness is abided to, right? And that is just our m tilde, and that is minus m tilde, then of course we have enclosed everything, right? This is the idea. All right, then there is such that we have that. And what do we do now? Well, by triangle quality. Well, do I need triangle inequality? It's kind of weird that I would need that. No, wait a minute. I didn't understand what. I thought that we could do that by triangle inequality, but it's not quite the case, I think. Just to think. Yes, yes. Yeah, I'm having schemes like in mind. Yeah, okay. We have actually not that, but we have that. I said the other way around. Okay. And that is of course bigger than an. And how did we use the triangle inequality? Well, just represent it here by 0. Right? So that is that sum here of the two absolute values is more than epsilon plus a, right? Because that is more than epsilon, that is equal a absolute value is equal a absolute value, right? And that means, well, we have estimated those infinitely many members of the sequence that come after an epsilon, and now take tilde, our supposed upper bound of the set of the sequence values, right? We define it as maximum of epsilon plus a, because that then is larger than that, because we take this maximum in particular between this element and between other things, so it is larger than all a n's that come after this, that come after a and epsilon, right? And then we take also here just max. So this in particular larger than all those of which we take max here. What things we take max of well, we just take n small equal n epsilon. And of course I might have taken also, oh well, let's do that to not confuse, but of course it's same because it's just max. I just made this max maybe a little bit larger, but in total it's just max that just total is just max that is larger than every single member of the sequence, because that is larger than all everything bigger or equal from the point and epsilon, and this is larger everything before that, and this is larger than in everything that is involved in this sequence value set. All right, this tilde serves as bound of the sequence value set as a bound. Of course, there are multiple bounds. As a bound of the sequence value set. Alright, so if a sequence is convergent, it is necessarily bounded. Right. And the contraposition is if a sequence is unbounded, then it can be convergent. And it is kind of, well, you might think it is obvious, but it is not necessarily that obvious. Because for our unbounded sequence, we can't kind of visualize all the behavior of it. It is kind of intuitive, but kind of also not so good to have. Okay, this contraposition is often used to just very quickly deduce that a sequence cannot be convergent. Okay, let's prove that. Recall the statement. We have a convergent sequence, limit, some limit a, and we have a null sequence, and then the product of the sequences is a null sequence. So this is kind of a special case of our main theorem that we are trying to prove now. But well, we need the special case to prove this theorem. But of course, after we have proved the theorem, that will result from it naturally. But we have to prove it first, because without that we just can't do the general proof. But after that, we can just always use the theorem, of course. Okay. Or perhaps we can, as I told you, but I just see that way, so let's do it like that. Okay, well, and it is anyway, it's used for lemmas. So even if there would be, even if there is a simple proof, well, it's not for nothing that we prove these lemmas. They are very useful for arguing with sequences, arguing topics of sequences, similar stuff. Okay, proof. We show zero. There is an epsilon element n. Well, probably already bored by this routine, or maybe not bored, but well, you are noticing that it's always about the same thing. There is an epsilon element n such that for n bigger. But of course, details change. Details change, but a lot of things stay the same. And this is really like that by proofs of sequences. But okay, not by all. We are now doing rather simpler stuff. The last thing will be really challenging, and we'll see how we do it. Okay. Now we show for epsilon bigger than 0. There is epsilon, then such that for all we have that in n bn. And I don't write minus 0, just write smaller than epsilon. Right, and this is really very simple because let epsilon bigger than 0. Then we just think about how we can estimate that. And we have a bounded sequence, and we have a nullsequence, which allows us to just... I think we need another lemma. Okay, well, whatever. Let's I think we need another lemma. Or maybe not. Maybe not. No, no, no. We don't need another lemma. Okay. Let's and epsilon and then be such that um well we have convergent sequence and nullsequence. So since A is convergent sequence, then it is bounded, in particular be such that well m divided by epsilon is bigger than n for all n. Okay, that's weird to think what I'm talking about. Bn is a sequence convergent to 0, right? Since it is a sequence convergent to 0, we find for an epsilon, we find for the epsilon such an epsilon. For n epsilon, we find such n epsilon, n such that for all n bigger or equal than epsilon, we have that because it converges to 0, and then from one point onward, bn minus 0 will be small, and that is bn minus 0 will have a small distance, and that means exactly that bn will have a small absolute value, in particular absolute value, small absolute value that is smaller and keeps being smaller than this particular newly chosen epsilon, right? Okay, where m is bound for the sequence a n element n. You recall that's the sequence, the bound, a bound of the set of sequence values. Okay, well, um, okay, that we obtain. Then for an epsilon, for n, so exactly for n bigger or equal exactly as an epsilon, have an n. Well, that you should prove again by yourself, lemma for exception. Again, just case distinctions, nothing special, just pure technicalities. Have xy equal xy. Proof homework. Okay. Well, everything is positive, so we can, without much thinking, estimate that. And we estimate that against what? Well, against one estimator of Bn for n bigger or equal than epsilon, so this estimator works. And of course, we have concocted that. Sorry, didn't mean that. I mean that. Because you see, I have concocted it exactly in a way so that. No, didn't mean that. I mean, I'd like to multiply that estimator by m, right? I'd like to multiply that estimator by m because that is the estimator of the sequence an, and that is exactly epsilon. Well, and if you are wondering why exactly, well, that's a problem that we have that here bigger or equal and we don't have bigger. Well, that's not a problem because we could just do that. This works for any epsilon bigger than 0, right? This works for any epsilon bigger than 0. And we just put here that just as well. Just follow through the argument and understand that it is valid. And then you see that we are really allowed to do that. And that is that. That is epsilon half. That is. And it was. It's good that I did it like that so that you understand that it doesn't matter how exactly there are some flexibilities in how to write and to think, right? So the story itself doesn't get influenced by some particular alterations, and you should see where such alterations are allowed because the context doesn't change. The context and the meaning doesn't change. Okay, just think about it, follow through this argument another time, and think why we can do that. Okay. It's really simple. It's about every epsilon, about the meaning of every epsilon. Right, and yeah, that shows that it is now sequence just by definition. The limit of a sequence. Okay, I think now we can go back to our reasoning. Maybe I should tell you how we come up with this proof. You see, we'd like to estimate that like that, right? And we know that we have that, and then well, we just know that we can control Bn, we can make it as small as possible, right? And we know we have that is bounded, so we would like, and we know we have that estimation something if we are able to estimate it by multiply something because we have everything positive, so it really works. And well, we just choose suitable things. And what suitable things? Well, of course, here we just know there's some bound, so we take this bound. We don't know about the bound anything else, right? But here we can control it as we like, as much as we like. And so of course it just asks to take something that scales the epsilon by the bound so that this multiplication gives epsilon, and this is exactly what is manifested here. Okay, this is how you come up with that. You look at that and you think, how can I change that, change the shape without changing the meaning? Of course, it is really obvious that I can do that. Okay, well, does it lead somewhere? Well, I can control that, and this is controlled already by a constant, and well, it plays nice together and gives exactly the estimate. This is how you come up with that. And having all those lemmas, we come to here and we recall that in our lemma, I remind you we had an to a, bn to b, so I mean convergent respectively, and we wanted to prove that an bn is convergent to a b, and we now arrived after adding an additive neutrality, we arrived at this expression for some index n. And I mean for some index n, meaning we choose such index, but we could alter that at each index with respective n's, because yeah, this is just depending only on n, right? So for each index it just works with respective index kept same for index chosen. All right. And well, we had that, and now we finally get that this goes to 0, right? And this is multiplied by constant. In particular, constant sequence is convergent sequence, because constant sequence, of course, just converges to the constant, right? You could check. Okay, you have that. and that is obviously smaller than each epsilon. Okay, yeah, so constant sequence converges to a constant, which makes the sequence, right? So, and here you have this nullsequence, so this is convergent sequence multiplied by nullsequence, and here you have your convergent sequence multiplied again by nullsequence, which allows you to see that this is nullsequence, right? But nullsequence, if that is nullsequence, that is nullsequence, and we can have nice estimates, respectively, for different and epsilon tilde. We have nice estimates. We can make it very small because that means being a nullsequence. I mean, make it very small in absolute value. Right, and then we estimate by triangle inequality, of course. Again, this is just an absolute value is equal this to an absolute value, and then this is more, we equal this with triangle inequality, and we can estimate the particular two terms, this term in absolute value, this term in absolute value, and this gives us the wish statement because we have estimated the absolute value of that against an epsilon because we can control both parts. Okay, let's do that. I don't know if we managed to do it here. I think so. I think so. And I'm just repeating what we did here, right? Let's so observe observe that a multiplied by b minus bn, a multiplied by b minus bn is a null sequence, okay, and bn multiplied by n minus an, bn multiplied by a minus n is a null sequence. Okay, that is just because those are obviously null sequences, which you can see just if you apply the definition of the convergence of those respective sequences. Okay. Let n epsilon be max of epsilon tilde, and epsilon head, and of course you know what an epsilon tilde and epsilon head for n epsilon head for n and epsilon tilde. I mean n epsilon tilde. Right, have how that we can control it by how what we would like is of course epsilon half because we have two parts to control, right? Okay, so we have that, and we have that. Right, that is convergent sequence, nullsequence, right? So Bn was convergent by assumption, and we have just discussed that this is nullsequence. Okay, and in for n bigger or equal an epsilon have, well, this is now just the manipulations which we have did here, and Bn, we just add a 0, right? A b minus and Bn, and our 0 had we form abn minus abn. To achieve that possibility to compare, we have had to add a 0 plus abn minus abn, which is exactly exactly what we like that, right? And now observe AB minus ABN is a, I'm using commutativity and I'm using distributivity, right? I put that and that together and use distributivity. And minus BN plus, could have immediately used triangle inequality, but okay, I'm merciful. Bn a minus an, just put those remaining together, right? A minus an or equal. Okay, let's make the exclamation. Let's make exclamation marks here more humble, and now we have that. And that is just triangle inequality, right? And now I use estimates, right? Because I have that bigger or equal maximum of those controlling points from which I can control it, and that is equal epsilon. And we have shown that for this chosen epsilon, we find an epsilon for such that for n bigger or equal than epsilon, we can control it by epsilon. Which finishes the proof. Okay, well, let's prove the third one, and this will be a huge challenge. This was like um, playing around, more like playing around compared to the third one. I'm not saying that it was simple by itself, but compared to the third one, it was just playing around. Okay, let's do that. And the third one is the quotient thing. Okay, we actually had a lot of lemmas and should keep them in mind. And actually, if I didn't already give you that advice, you certainly should write down the things I do. Just to watch video is, of course, not enough. You have to write it down, and even more, you have to be able to reproduce that. And I don't mean reproduce like remember. You have to be able to reproduce the logic, to reproduce the story, to retell the story that I'm telling in proofs and about objects and things like that. And not necessarily in my own words, just in your own words, but it would be weird if you would retell it in my words, retell this story from its meaning. Its mathematical meaning should be proper, and maybe you will correct some mistakes that I make. I don't know, but the mathematical meaning should be proper. It's about that. It's not about you retelling this story in my words. Not at all. And that would be weird and not the thing we are aiming at. Okay. Well, we have the third one. And this one, well, it's challenging. Okay, third one, proof. Okay, let's think. And here I don't know how. I'll be honest, I don't know how to do that. And I mean, I completely do not know. I think that I do completely not know, but no, let's let ourselves surprise ourselves. Yeah, but we'll look at that and we figure it out. No problem. Okay, well, we had quite a lot of lemmas. Have not thought about that in the beginning that we would have many. Okay, well, I mean, to just prove that, we had to look at a lot of things. Okay, but the third one is even more. The third one requires thinking that is not just guided by structure, but it is. Okay, well, what we have to prove actually is that. Okay, well, yeah, don't we don't do the proof yet. We do side thinking. Right. Well, of course, most natural thing like you'd like to use what you have here, right? So you kind of would like to of course we need an estimate, but okay, let's just spare ourselves some notation. Just think of that as being there in some case, in some sense. So the most natural thing when you think, when you have two fractions and you want to use what you already have, well, you make the products, right? That makes sense. But what comes after that? Oh, that is a n b. That is a b n, right? So if we could control that and that somehow in connection, that is, we actually would like to have that, right? And that we can control. There is no problem because that is going to A, this is going to B, so this going to AB, this going to AB. No problem. That we can control because those sequences have same limits, and you can prove lemma. I won't even state it. It is just something that I won't state all lemmas anymore because some things you just have to see that you have to derive them and you have them to derive them. But this is not the difficult part of it. That if two sequences have same limits, then the difference. Okay. You can just deduce it from the first two things, right? Because you just use that this has this limit, this has this limit, and then you use the first one, and yeah. And yeah, I discussed that case specifically. So yeah, this is not a problem. This will be nullsequence. But what is that? Uh, yeah, the problem is that thing. We don't know anything about it. We actually know what it is. That is inverse of BNB, right? We don't know how it behaves. We don't know it at all, right? All right. Well, but what can we do about that? Well, we know, like, if it is inverse, well, what can we do? Well, we can do that. Makes sense, right? And what we kind of know, well, if that now behaves badly, because the only thing that we actually need, we don't need that this is somehow convergent or something. We just need that it is restricted. Restricted, meaning that it is bounded. It is bounded, and then it's okay, right? Because we would have bounded. Okay, not necessarily. We would have bounded sequence multiplied by nullsequence. Bounded sequence is not necessarily convergent. Okay, that would be another lemma. And I don't know yet if it works. So it's not like earlier. Okay, lemma. I mean, the lemma works probably, but uh, okay, the lemma works, but if we can prove it, I'm not sure. I mean, it might be that logically we will require other stuff for that. I don't know yet. I think no, bounded sequence multiplied by nullsequence by nullsequence. Yes, no, it's very simple. It's very simple. It's convergent. It's a nullsequence. So we don't need convergent sequence multiplied by have we already stated it like that? I think no. But we should have stated it like that because uh, you see, by convergent sequence multiplied by nullsequence, we used to show that it is a nullsequence only the boundedness. We didn't use the convergence. So of course it is true. So this lemma is true. But yeah, the question is if we can show boundedness of that. So what we really need is just boundedness. And what we have is with property just by definition of inverse, right? So we should show that if it is unbounded, then we have problem with this property. That's basically the idea. But what do we know about this sequence? Well, we know that this sequence converges to b squared. Okay, well, I thought that it is difficult, but it is not difficult. Okay, huh? That's funny. Okay, so assume B and B is not bounded. Okay. Well, assume B and B. Wait. But that should converge to B square, and that should converge to 1, right? So B and B multiplied by 1, B and B trivially converges to 1. Assume that this is not bounded, then it cannot converge to 1. Of course, we haven't shown it yet, but I mean, the thinking goes like that. Or it could go like that. This goes to B squared, this becomes unbounded. Well, then from some point onward, we could say that it is approximately B squared. And now, if this is not a bounded sequence, what does it mean? Well, if from some point onward it would be bounded, then it would be bounded at order. We could say, use the same trick. We could use the same trick that we used to show that convergent sequence is bounded, right? Okay, maybe you recall, maybe you should recapitulate that. We had that just recently. All right, we had that in the proof of convergent sequence multiplied nullsequence is actually a nullsequence. We have proof there in between that convergent sequence is bounded, and it was really simple. We used that trick. So if it is unbounded, then it is unbounded infinitely. So for each n, we find another point from which it is, at which it is, at which, what I'm trying to say, if it is then unbounded, then it is unbounded infinitely, meaning that no matter what starting n we take, from the starting and onward, it is unbounded. But we don't even need that. We just need that it is above 1. So we just take 2, and we have that for each starting point onward, we find a point above 2, and when we convert this to 1, it's impossible. Okay, that's much easier than I expected. I thought that this will be a real challenge. But no, it is not. Okay, oh, funny. That's funny. Okay. Oh. But of course, that was not rigorous writing that down. That was just I have shown you how I came up with a proof. Right now, with a proof that I will now write down, and I really have expected that to be a challenge, but no, it doesn't seem to be a challenge. That's weird because I recall that I don't recall the proofs, but I recall that the proofs of that actually took took some work. I mean, took some work. They wrote 2 pages or something, but and I mean 2 pages with some not that trivial manipulation. But maybe I'm confusing that with something. Yeah, I don't know, but yeah, it certainly doesn't seem that difficult conceptually. Okay, I don't know if you could follow that, but now we will write it down cleanly, and then you can follow that, of course. Okay. Well, here is free proof of free, and here we continue. Not here, we continue, and continue here. And that you could do as homework, that lemma you could do as homework, proof homework, or see proceeding in the lemma convergent sequence multiplied by nullsequence gives nullsequence. Okay, well, Okay, so let's do the proof of the fruit one. Let x1 0, then have to show that I think this is the point where we don't need to actually show that explicitly. We can just use our lemmas and do it on a higher level of structure, so to speak. Okay. Yeah, and we should do it on the higher level structure so that you get used to the switching of levels. When in maths we have sufficiently many properties that point from the lower level structure to higher level structure, then we can start to argue on the higher level structure immediately. Okay. For n element n, and that means for all n element n have n divided by bn minus a divided by b is equal to a and b minus a bn, and we divide by p and b. Okay. Well, observe that a and b minus a bn is a nullsequence. We have discussed it, and it is simple, right? This converges to a b. This converges to a b by the point 2 in the theorem. This converges to a b by the point 2 by the point 2 in the theorem, and they have same limits, right? And then we make the difference, and the difference is nothing than multiplying by -1, so that converges indeed to minus AB, and then we add the sequences by 1, and we get a sequence conversion to the sum of the limits, so AB minus AB is equal to 0. Okay. Then show that 1 billion B is bounded, and use lemma exactly that lemma that we stated. Of course, we haven't stated it for nothing. Okay, the lemma bounded sequence multiplied by null sequence is indeed a null sequence. Okay, well, ensure that this is bounded and use the lemma. Okay, let's see. Yeah, that was the arrow to the lemma. Right. Right. Well, just observe that B, 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 B. We assume that that is not zero and that is not zero for anything, so we know that this is not zero, this is not zero, so it's a valid sequence, right? Converges to 1. assume, so we assume the opposite of what we'd like to show, and show that assuming that leads to a contradiction, and then we will not write, and assuming that means that it is not the truth, and then the opposite of what we assume is truth, and we have assumed the opposite of what we'd like to show, so the opposite of the opposite of what we'd like to show is what we'd like to show, and so what we'd like to show is true. Okay, now assume A and B is unbounded. Claim that means for n element n, and that is for an arbitrary n element n, we find n bigger or equal n with 1 b and b is bigger than let's see, bigger or equal 2. That is my claim, and I'll just observe our rise. If it is not true, that if it is not true, meaning that our rise we find children and then such that oh n bigger or equal than children have 1 divided by r, and of course that with for all bigger or equal to n, we have that this members of the sequence of that sequence are bigger or equal to. Okay, such that for all n bigger or equal to tilde have b and b smaller than 2. And then we show that it is bounded. And how do we do that? Well, very similar technique to which we already used. Maximum of 2 and maximum of 1 b0 b, just listing those sequence members explicitly, right? B and tilde b, right? So I have to go to and tilde. I have to take this maximum. This is finite remaining, so the maximum is fine, and from the here onward, it is bounded by that, right? Is an upper bound, is a bound, it's generally bound. General bound is it is indeed general bound. We have everything in absolute value. So yeah, M is a bound. So indeed, we claim it's true because otherwise we would find into the element n that would provide us in total the upper bound for the sequence. So if we assume that it is unbounded, that means that for an element n we find such n equal n with 1 en, and otherwise just break it in, because this is just the justification for this claim, right? This is the proof of this claim, but it is simple, so let's break it in. Okay, simple because we have already seen that recently, right? Recall that. Okay, now assume that it is unbounded, and we have that claim, which turned out to be true. Then Um, let now recall that this absolute value thing, that it is converges to absolute value squared. And how do you know that when a sequence converges to something, this sequence in absolute value converges to limit to the absolute value of the limit? Well, this you just know by if you have that sequence an converges to some a, then we claim is that an absolute value converges to a absolute value. And how do you have that? Well, you just think, well, when I have that, then that means that I have actually to show that, right? And well, okay, let me do a quick. That is actually a useful theorem or whatever. I forgot how exactly it is stated, but I think it is that that for each and everything we have that comparison. I mean, for any true real numbers x, y. I'll state it rigorously in a second when I will establish that it actually works. Okay, well, how do we do that? Well, you see, we have two cases, right? We have the case where that is positive and where that is negative, right? Case is smaller than 0. Case that is bigger or equal 0. That is well. When we have that is bigger or equal 0, then we just have that and this is exactly that thing, right? And that results x minus y plus y bigger or equal x. Okay, so that we just have by triangle inequality, right? And then we for this case, when we took such numbers for which that is literally true, we just have that from triangle inequality, okay? Now take such numbers for which that is true. That is, we have minus x plus y. Well, then again, we have to show that this is small or equal this absolute value, and well, this is obviously true because you have that triangle inequality again, because recall that this is nothing else. So you see how useful the triangle inequality is actually. Oh, so triangle inequality because we brought just plus x absolute value, right? We used here y plus x is equal that, right? We added 0, we have that, and then by triangle inequality we have that estimate, right? Where we have plugged, we have taken out of each other x and x minus y, and we had those, and we have that estimate, so indeed that is true. Let's state it as lemma. Lemma for x, y, element r have I think it's usually called inverse triangle inequality, but I'm not sure. I have rarely met that, but it is used, but not that often. have inverse triangle inequality, that is that we have just established that, right? If you didn't understand that, then just think how to prove that, and it is a good exercise in understanding the absolute value, and especially treating that with case distinctions and corollary. Okay, that works. And when you will actually probably does not work in the absolute value. No, not at all actually. Okay. Okay, corollary. If the sequence say n element n converges to A, then, and this is a good homework because you can think about some things. I have actually already explained it here, but if you didn't understand that, well, do the homework. Okay. Then this in absolute value converges to this in absolute value. Okay, proof homework. And here to proof homework. And don't complain. I did a lot of proofs in this lecture, and these proofs are rather small, and I have actually written down the proofs. So. Yeah. Okay. So then we know that from those lemmas above, we know that B and B in absolute value converges to the limit of B and B in absolute value. That is, it converges to B squared. Just recall the setting or read it up again if you need to. And that allows me to use the convergence definition of a sequence absolute value of B and B, by which I mean then let let what? Then let epsilon bigger than 0, and then there is well, we didn't use an epsilon, right? No, here we didn't use an epsilon. Okay. Then there is an epsilon and then with for n bigger or equal than epsilon, we have that we b and b minus b squared here is smaller than epsilon. Okay, well, which actually okay, well, that is smaller than epsilon, and we have that this is bigger or equal to. Okay, then and put both together. I mean both, meaning that this is infinitely unbounded, meaning that for each n bigger for each n element n, we find an n after this n such that we are bigger or equal to, and that this is convergent, so we can estimate that very neatly, right? So then well, let's take a special one. Then there is let's not take epsilon, but take something concrete, right? So what we do is just taking epsilon b. Okay, I think 1 would be already good. Right. I think 1 would be good. Because now we have what we have that unbounded, right? And I would like that to be oh, that approaches b squared in absolute value, and that is unbounded. So what I'd like to have would be that this is always bigger or equal. Okay. I don't actually like 2. I like let's think. Well, if I have that, then I have that, and I would like to have that this is certainly smaller than something. Okay. No, I'd like to have that this is more certainly bigger than something. Okay. Then recall again how we deal with absolute value. We have then that b and b is certainly bigger than the limit minus or epsilon. Okay, well, and now we would just like to have, so that's exactly the case for the, or if you want to have that, then it would be considered that, right? And we would turn it around. I mean, I consider the minus case, I turn it around just to double check myself. Would like to do that explicitly. Okay, then we would have that, and minus case would be plus, that minus, that would be minus, right? So that would be minus, and that would be minus, that would be plus, right? And the sign would be turned around. So I'm noticing that I don't like the idea with 2. We need something specific. But okay, this will work just the same, because we could take any lower, or any potential lower bound, right? So what I would like to have, I would like to force it to be too large, so larger than 1 of that quotient, and that would be b squared minus 1. We could just take b squared minus 1 actually. I think, yeah. Oh no, we actually need that. Okay. B squared minus 1. Yeah, now b squared could be something that we don't. So what we'd like to have now would be b squared minus 1 if b squared is not equal 1, because so otherwise we would have trouble. We would have to divide by 0. If b squared is not equal 1, otherwise let's say b squared minus 2, because if it is equal 1, then we would have here something bigger than that. Right. Well, actually, I don't like that either. I'd like to have something positive, right? And I'd like to have that positive because I would like to multiply two things, and I would like to have inequality be preserved, right? So we just take that thing, which is of course just b squared divided by 2, but okay. Okay, let's do exactly that. Let's do exactly that. Certainly smaller than that, right? You can do the comparisons using the axiomatic for your numbers yourself, if you like. You need to do that. So, of course, I would have written it more neatly, but okay, I'm not doing that. So that is b, b squared in absolute value divided by 2, and then I take my epsilon. There is an for, of course, I could have written that it's just 1/2 of that, but okay, it doesn't matter. And this also doesn't matter, as you know, because we have already had that b squared is that absolute value of b squared is same as absolute as the absolute value of b to the power of 2. All right, okay, here I write that because it doesn't matter. Okay, so we are telling the story, and the particulars like that, they just do not matter. Okay, well, okay, that's actually nice because you see, we took that, and then we took that, and then we obtained exactly that, exactly what we wanted, because we'd like to have here exactly that in order to it actually be bigger than 1, right? So then putting both together, then for n, so for n, which is from where both we have that estimate, so that is certainly bigger than that, right? And we have that estimate gotten from unboundedness that is bigger or equal than that, right? Reciprocal 1 divided by what we had here, right? Then for n, starting where both conditions are true, we have simultaneously, and let me maybe write another time, have for okay, it is a little bit more tricky. We have that here exists because here we just had the condition that for okay, no, what we want to have that our limit is not 1, right? So the only thing that we have to show is to show that we constantly fall out of line, and we could never be always in proximity of our limit, right? How do we do that? Well, that's simple. Yeah, okay, I see that. Okay, it is difficult in sense that we have to make a lot of adjustments. I do not want just to have that we are bigger than 1, because being bigger than 1, we could yeah, okay, no, it works because we actually have a constant. It is not just we have that the sequence is constantly equal to 1. So yeah, we just have that. If that is unbounded, okay, then there is then there is, I mean, we go now to look for what we'd like to have for a certain index that we'd like to have. We go beyond an epsilon so that this estimate is constantly valid. Okay. Okay. We go beyond an epsilon, and from there on, from there on, we look for such an n. So already after that, so bigger or equal an epsilon, such that this is true, right? Okay. And that gives us that this product of that with the absolute value of b and b is bigger than 1, which is impossible because, well, this sequence that is that product must be constantly equal to 1. And constantly equal to 1, by the way, is that. So that is constant sequence 1, and this sequence is constantly equal to 1. But okay, this limit consideration we do not necessarily need, because assuming that it is unbounded just leads to that sequence not being constantly equal to 1, which it should be. Alright. Then there is, but we only need that there is such one, right? There is n tilde n with, well, simultaneously b and tilde b bigger than b, and that is strict inequality, right? And that's 1 divided by b and tilde b being bigger than, bigger or equal, actually, they are bigger or equal, and that divided by 1. But then for this and tilde, we have that b and tilde b and tilde b is strictly bigger than the product of those, meaning bigger 1. Contradiction to b and b and b go 1 O and n. So it is impossible when we have the numerator controlled that the denominator just just goes to something uh, infinitely high, because, well, that is really comprehensive, because if the if the numerator goes to something that is already that's actually interesting. If it is unbounded, then we should have that. It's interesting that the contradiction that we get is actually by this being bigger than something. Because unbounded actually would mean, that is surprising. Because unbounded would actually mean that this becomes small. That is a little bit surprising. So we are assuming that this is unbounded, and then actually we should be too small, not too big. It should be too small, because that would actually go eventually to 0. Because if we have such a situation that this kind of accumulates around some b squared, right? That accumulates, it goes in this direction, accumulates here, and we divide by something that is unbounded, so that goes to here, or maybe some way it goes also downward, but more reasonable would be something like really large, because it is unbounded in the something like really small, because we divide by it, right? And so that's really funny that we get actually an estimate that is for something being yeah, okay, I understand. We assume that this sequence is unbounded. No, not the denominator, but this sequence. Okay, not the denominator itself is taken as a sequence, of course, because that we know that it converges, but this sequence is unbounded. And then, of course, It makes sense because we multiply such a sequence that accumulates here by we multiply by the sequence that goes to infinity. And then, of course, we get too large, not too small. Okay, well, hence B n B n element n is bounded because that our assumption that it is unbounded led to this contradiction. Hence, that is bounded. And what does that mean? Well, that means we have a bounded sequence and we have a null sequence, and we use that lemma to have that this is null sequence, and this is null sequence means exactly, you can take a look at that, that this is limit of this sequence, right? Because, well, another lemma, but this is like a lemma, this is lemma redefinition. Lemma A is limit of a convergent sequence A n element n if A minus n element n is a null sequence. Proof, of course, homework, because you have just to write it down and you have to see that it is same thing. Same thing literally. You do not need any thinking steps, actually. You just need to evaluate the definition and to see that it is same thing. Right. But of course, write it is the two implications, one way, another way, and of course it's perfectly valid, and it's normal to struggle with it because it is so much of abstraction. But yeah, remember that you have to see the mathematics speaking, and those symbol juggling, that symbol juggling is just how it is conveyed to us and not what mathematics is. What mathematics is beyond that and is just conveyed in that way. And this is the only way to convey it, unfortunately. But yeah, this is not mathematics. Mathematics is beyond it and far deeper within it. And this is just how we give it shape, what mathematics is. But mathematics truly is much beyond everything what we can see uh, that way. Okay, but we feel it, like we can follow the flow. Okay, so we have that, and we have then that this is nullsequence because we multiply a bounded sequence as we now establish with a nullsequence. So this is nullsequence, and that establishes that an divided by bn converges to ab, and which shows, let's use a fancier word, which establishes the claim. Okay, I think today it was a lot. We had theorem after theorem, lemma after lemma to prove this theorem. But yeah, just work through it. And always remember that mathematics is not about juggling with symbols. It is about much more. Juggling with symbols is what gives it form, what gives it speech, but it is not that. We can see windows into mathematics through that. through our thinking, engaging with that. Our thinking, engaging in telling the story, and simultaneously listening to a story, which is, of course, ultimately told by the mathematics, which uncovers in our minds. So this is kind of UI creator and UI listener to a great melody. Always remember that, because this is the only right way, the only this is the only approach that psychologically does justice mathematics in application to your mind. Other approaches are, I mean, other approaches compared to this approach, meaning approaches that denounce mathematical essence as something just being conveyed in this language of symbols, but being by something far beyond that, and being not about those symbols, but the symbols being just means to convey it. Other approaches are just less rewarding. Let's put it like that. Less rewarding, and the they are less rewarding, and they make you forget the main thing that you can actually enjoy to the truest, even if it is difficult, even when you have to do a lot of steps, when something doesn't work, when you see that it is mathematics speaking to you, that it is you engaging in your mind with this world who is trying to tell you what it has to tell you, but by which you yourself have to get active to um, to engage with it, to let it uncover within yourself. This is the way how it should be perceived in order to really touch it within yourself. And when you adopt this approach, the psychologically, I don't mean like, of course, you struggle, that's normal. I also struggle in my studies, that's completely normal. But this psychological approach to mathematics, it turns out that it is really important, and it increases the measure of pleasure and joy and everything like that tenfold and hundredfold when you uh, just psychologically explain to yourself what mathematics really is and what it isn't. But okay, it's just my approach. Me telling that it is the only approach is of course nonsense. But yeah, it's like this is one of the keys to see what it is really about. Let's put it like that. And you have to understand that this throwing around symbols, that it is auxiliary. It is auxiliary. It is not what it is about. It is not at all what it is about. It is just the form. It is the form. Let's put it like that. This is the form. It is not the essence. It's like we people identify often this the essence with the form, but it is because we don't know better. But nonetheless, we can, when we are mm, attentive and are sensible to that, we feel this essence speaking through the form. And this is why you can really enjoy mathematics, because actually essence speaks through this form, even in that incomplete, in imperfect shape. The essence speaks to us. The essence speaks to us, and the essence leads us and lets us see the story that is uncovering in our mind, by us also being creators of that, in that we allow it to uncover, but in that we simultaneously, in our own perceptions, are truly the creators of that. But yeah, mathematics is far greater and far beyond that. And remember that when you look at such technical proofs that contain many steps, that it is not about that. It is that the way to engage with it is that, but it is not about that in its essence. Okay, well, we actually did a lot. And next time, mm, oh, next time we will start to really engage in structural setup of video numbers. I think we are that far now. In structural setup of video numbers, sense of some limiting processes, how real numbers relate to that in their video structure and things like that. Yeah, that will be fun. Okay, yeah, today was also fun, but that will be so really fun. Okay, then enjoy then.